As I wait a minute or two, does anyone have any questions, concerns, things they want to talk about before we get started? Usually how the beginning of a semester goes. Nobody talks. Hopefully you can all hear me okay. If you can't, let me know. But you're going to see me and Dr. Fry both are going to just be like, okay, we're going to ask questions in the class. We're going to stand there. The thing is that students eventually realize that we're more patient than them, and they eventually answer the question. So be prepared for that. I don't know who you guys have it. If you have engineering, you have me. If you're in regular Gen Chem, you could have me or Dr. Fry. And don't be intimidated by either one of us. We're both really, really nice. We're both really helpful. We both want you to succeed. So let me choose the right pen. Trying to work on I'm teaching a summer class right now, and I'm trying to work on their final. Writing on my iPad with a regular pen just isn't going to help you nor my screen. So I'm going to go ahead and get started. I know that you've spent some time this week talking about stoichiometry with Drs. Green and Janesco, and I'm going to continue that path. I'm going to talk about some chemical reactions. I'm going to talk about balancing reactions a little bit, and I'm going to talk about some stoichiometry, just a little bit more maybe advanced than you've seen so far. I know depending on what kind of question you've done, you've seen some different difficulty levels, and that's kind of what I want to continue this week. Take me off the screen so you don't have to see me on the recording at least. Okay, so first thing I want to review is chemical equations. I know that you guys have seen this, okay, because I watch, granted at 2 times speed, but I watch what Dr. Green and Dr. Janesco do with you guys to make sure that I'm not covering the exact same content. So I know you've seen chemical equations, but I want to just review it quickly for those that maybe weren't able to attend one of their sessions, or those that just need a little bit of a refresher, and just so we can make sure we're all on the same page. Excuse me. So all a chemical equation is a way for us to symbolically represent what is happening in the reaction itself. Chemistry has a lot. We keep saying this in boot camp, I know, and we'll say it in class too, but chemistry is a language, and you're learning to speak this language. And part of that is constant practice. And I know Dr. Green covered this with you guys as well, but a lot of you are going to be taking chemistry and biology this fall. And it doesn't matter if it's Bio 1 or Bio 2. It truly doesn't matter. They're hard classes. They just are. Students will tell you they're weed out classes. We're not trying to weed you out. Contrary to popular belief, we really would love nothing more than every one of you to succeed. We truly would. They're just hard because the material is hard, because you're learning a language that you may or may not have spoken before. And statistically speaking, we let students with a C- or better continue on to Chem 2. Statistically speaking, students that receive a C- in Chem 1 do not succeed in Chem 2. Dr. Fry knows the exact stats. I would have to ask her, but it's very few students that will actually survive Chem 2 if they don't do well in Chem 1. We want a good basis for you guys so that you're ready for what's coming, okay? So make sure, I know Dr. Green covered already, make sure that you're planning your schedule out and that you guys are studying every single day for this class. You're studying every single day for biology. Some of your other classes, you may not have to do that. You'll hear other students in other majors or even parents say, oh, your first week is silly week, it's syllabus week, not in chemistry. And so I just want to kind of state that again. I know I've said it before, but state it again so that you guys are prepared for what's coming. Doesn't matter if you're engineering major, if you're in Chem for engineers or Gen Chem, we start the first day. So anyway, chemical equations, again, symbolic representation of what's happening. So when you're writing your balancing chemical equations, we have to do this. We have to balance them so we can correctly calculate what's actually going to react or how much is actually going to be produced in a chemical reaction. By balancing the reaction, it's our bookkeeping. We're keeping track of, we've got the right number of molecules on each side of a reaction. A reaction can represent molecules, particles, or moles. Most often we're going to deal with it in moles, but we could simplify it down to, like in the picture here, we've got CH4 reacting with O2, forming CO2 and water. I could simplify this down by saying 1 molecule of methane, which is CH4, reacts with 2 molecules of oxygen to produce 1 molecule of CO2 and 2 molecules of water. I don't usually say it that way though, because 1 molecule is a really, really small amount. Instead, we're going to be dealing with moles. So same thing, 1 mole, 2 moles produce 1 mole, 2 moles. We have to have it balanced so you're doing the right stoic. And so the chemical equation, again, that symbolic representation, reactants are always written on the left, products are always written on the right, the arrow is always in the middle. No exceptions to that rule. In Chem 2, you're going to deal with 3 entire chapters. It's a big portion of Chem 2 where we deal with reactions that are called equilibrium reactions, meaning the reaction can go forwards and backwards. We still treat the chemicals written to the left of that arrow as your reactants, the chemicals written to the right of the arrow as your products. If we reverse the reaction and go the other direction, then our products and reactants have reversed. But just for standard language, reactants are always on the left, products are always on the right. So reactants are the substances that are initially present. It's what you're consuming during the reaction to make those products. Your products are what's being produced within your reaction. So the symbols that we use, you're going to see this as well. And this comes into play in chapter 4, but I know it may seem, oh, it's chapter 4. Chapter 4 starts in, I believe, week 3 for my engineering and my Gen Chem classes. Dr. Fry will do chapters 1, 2, then 8 and 9 and come back to 3 and 4. So she'll probably cover this by week 4, maybe week 5 at latest. So it's pretty quick in first semester. We want to get through the relatively easy stuff, which we covered so far in boot camp, to get to the nitty-gritty of chemistry. But you will see symbols used throughout the equations, and you need to start getting comfortable with these symbols as well. So the main symbols we use is the G, the L, the S, and the AQ. Notice that these, I'm talking about the ones here. They're all lowercase letters, but they're telling you the state, physical state of the chemicals that I'm dealing with. So if I have a gas, I'm going to write a lowercase g. If it's in a liquid phase, I'm going to write a lowercase l, solid phase, lowercase s, and then AQ means aqueous. Aqueous means I have dissolved that in water. And we're going to spend more time talking about that in chapter 5. But if something has been dissolved in water, like salt water, if I put sodium chloride in water, it doesn't exist as sodium chloride anymore. It exists as sodium ions and chloride ions. And so we write AQ to represent that. You may also see little things like the triangle or HV. If you see the little triangle, if you see an arrow with a triangle above it like this in a chemical reaction, that just means that heat has been added to the reaction. And so some reactions require heat. Sometimes we specify it, sometimes we don't. You don't have to worry about it, but it just means heat. If you see an arrow with an HV on top, or actually that's not even a V, it's called nu, it's a Greek letter. It looks like a V by the font, but that just means light has been used to activate the reaction. So light is required for the reaction. You may also see catalysts written above the arrows. We see that pictured here with manganese oxide above a reaction. Catalysts are going to be covered more in Chem 2 under our kinetics chapter. It's latter half of Chem 2, you'll cover catalysts, but catalysts are not actually reactants because they're consumed within a reaction, but then they're regenerated by the end of a reaction. So they're not actually consumed permanently in a reaction. They're not considered a reactant. So we don't write them in the balanced reaction, we write it above the arrow. So you may see things like that as well. So by this point in the semester, I know right now in boot camp, we have not covered naming. We've given you some tools to name. We've given you some videos that you can watch for naming. I know Dr. Green has her videos out. I put my videos up on the discussion board as well. We recommend you start practicing naming now. We don't cover it real heavy in class. I do more I'm going to have students be covering it outside of class and then practicing in class with activities. And so it's covered pretty quickly and you just really have to just pick it up. But we want you to be able to take those names and go down to your chemical equation, your balanced chemical equation. And that's an important part of what you're going to learn in this in Gen Chem is, again, all back to that language. I need you to be able to say these things react with their chemical names, but understand in your mind, see what's actually happening. So for an example, let's go through this one. Aluminum metal reacts with air to produce a white powdery compound, aluminum oxide. Now, I want you to walk through these steps until you can get this down really quick on your own. And pretty soon you're gonna be able to do this on your own really fast. If you already can, that's fantastic. First, you're gonna ask yourself, what is reacting? Well, it tells me right here that aluminum metal is reacting with air. Now, when I say air, I realize that air is actually comprised of multiple things. We've got oxygen, argon, CO2, nitrogen. Depending on where you're living, there could be other things present in your air. When we say it's reacting with air, it's reacting with oxygen. Why are we not saying oxygen? I don't know, to be honest with you. I didn't make the question. I took it out of your textbook. But we're implying without saying that it's reacting with air. There are a set of elements that do not exist in their most stable, or as their most stable state, do not exist as single elements. And so pulling this up really quick, 1 second. This website I really, really like, ptable.com. see if I can, sorry, get it to, I was trying to get it off the actinide series, but if I can get the colors back there. I like it. It's pretty, it's colorful. I can click on any element on this table. So again, ptable.com, I can click on any element on the table and it will tell me all about it. I recommend always having periodic table with you printed, have one physically printed. Truthfully, I recommend using the one that we're going to post in your course shell in D2L for your classes, because you're going to see that's the same one you're going to have in assessments, so you can see what information you have, because we don't give you everything. We don't give you names on your periodic table that you're going to have in class. But there on this periodic table, there are a set of elements that don't exist as just individual atoms in their most stable state. We have 7 diatomics and we have 4 what we call polyatomics. And so when we get to class, I'm going to teach you the trick on it as well. And I'll write these down on the other side just a sec, because I can't really draw all over this thing. But one of them is hydrogen. These are my diatomics. I have 7 of them. There's hydrogen. And then the other one are easier to remember in some ways because they form a number 7 on your table. They start with atomic number 7. I've got nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So if you look from the nitrogen to iodine, it's forming a number 7 and it's starting atomic number 7. Then I also have to just remember hydrogen. But within this 7 here, so within this gap here, I've got a little square here between phosphorus, arsenic, sulfur, and selenium. These elements actually like to exist as polyatomics in their most stable state. Phosphorus and arsenic like to exist with 4 atoms of itself bonded together. So P4 and AS4 is its most stable state. Sulfur and selenium like to be 8. So S8 and SE8. And those you just have to memorize. So my diatomics, I've got H2, N2, O2, F2, Cl2, Br2, I2. Did I write all 7? Yes. Okay. And then my polyatomics, I've got P4, AS4, S8, and Se8. So unless I otherwise specify, if one of those things are reacting, it's actually in that form. It's as a diatomic or polyatomic. So when I say reacting with air, it's actually reacting with oxygen, which is a diatomic. So it's reacting with O2. I ask what is being produced, and it tells me producing a white powdery compound, aluminum oxide. Then I have to ask, what are the formulas of each reactant and product? Well, it's telling me aluminum metal. Aluminum is not one of my diatomics or polyatomics. So aluminum metal is going to be aluminum, just aluminum, Al, and it's going to be a solid phase because it is a metal. The only metal that is not a solid at room temperature, and this isn't specifying a high temperature, is mercury. We've got oxygen. Oxygen is in the gas phase. How do I know that? Truthfully, just intuition, because I'm breathing it in all day long. That's part of that comes from just intuition of students just kind of backing up being like, oh yeah, oxygen is definitely a gas. And then it tells me aluminum oxide. Now, you will know naming by this point in the semester. We will have covered naming already. So we'll know that aluminum has a 3+ charge and oxide stands for oxygen, which has a 2- charge. Ionic compounds have to have a neutral overall charge. In order to do that, I must have 2 aluminums to 1 oxygen, or sorry, 2 aluminums to 3 oxygens. It's also telling me white powdery compound. That word powdery is suggesting it's a solid. So I know I formed a solid. So I'm going to write the formula for each species out. I've got aluminum plus O2, give me Al2O3. I'm going to write the phases into the reaction. Al solid plus O2 gas, give me Al2O3 solid. And then I'm going to balance the equation. And so if I look here, I've got aluminum and oxygen. I can start with either one. I'll be honest, when I've got an oxygen here of 2 and an oxygen here of 3, I know I'm going to have to go to the lowest multiplet. So you can't leave balanced equations and fractions, by the way. There is one specific case that you are required to leave fractions in your balanced equation, but that comes in our chapter 7 in thermochemistry. And it's a specific definition that we use, which requires fractional coefficients. Otherwise, in Gen Chem, do not leave your balanced equations and fractions. I know in other chemistry classes, they may let you because mathematically it works. Do not do that in Gen Chem because it's not correct for the technical way of doing balancing equations. And Dr. Fry and I will not accept fractions. I've got 2 and I've got 3. I know the easiest way to do that is to multiply them to get that common factor. So I'm going to put a 3 in front of the oxygen here and a 2 in front of the oxygen here. That's going to give me 6 oxygens on each side. I know I need a 4 in front of the aluminum here. The way I personally do this is I then, if I was actually balancing, I would have written this out, but there's not space on it. But I write all the elements below the balanced or below the equation, and then I check to see if it's actually balanced. On the reactant side, I look and I have 4 aluminums. Here, I've got 3 O2s, which means overall 6 oxygens. On the product side, I've got 2 Al2O3s. So that means I have 4 aluminums and 2 O3s, meaning overall 6 oxygens. So my reaction is balanced. Another thing we want to talk to you guys about is combustion analysis. So we're going to talk more about reaction types and predicting reactions in chapter 5, which comes next week. But one reaction that's introduced in chapter 4 is combustion. You are responsible. It doesn't matter if you're in regular Gen Chem or engineering Gen Chem. You are responsible for understanding and be able to predict combustion reactions. You should be able to predict the product of a combustion reaction. So combustion is when I burn something. And if I burn a hydrocarbon, hydrocarbon just means a compound that contains only carbons and hydrogens. So like this compound here, or a compound containing only carbons, hydrogens, and oxygens. And we have a series of compounds that are like that. There's alcohols, there's aldehydes, ketones. There's a lot of organic compounds that only contain carbon, hydrogen, oxygen. Think about your gas tank. Okay, that's carbons, hydrogens, oxygens burning. If you undergo complete combustion in the presence of oxygen, you will form CO2 and water. If I ask you a reaction, I say this reacts, this is completely combusted, that means that you are reacting something. So if you see the terminology, complete combustion, I would have to give you one reactant. You would know that is reacting with oxygen to form CO2 plus water. Every time, no exceptions. Complete combustion, the products are CO2 and water. We also have incomplete combustion where the products are CO and water, so carbon monoxide and water, and that's due to an insufficient supply of oxygen during the reaction itself. The reason I mention that is because as a human in this world, you should know that. You should know that, we add ethanol to your gasoline to encourage complete combustion. You should know that catalytic converters, which unfortunately keep being stolen around Fort Worth, probably everywhere, but around out of the vehicles here. Catalytic converters are used in cars so that when your gas is burning, you're increasing oxygen production to encourage complete combustion, because we can deal with CO2. We can't deal with CO. CO is what's going to kill you, is poisonous to humans. So you are responsible for the reaction for complete combustion, but I want you to understand the difference between complete and incomplete, just because bottom line, you should care as a human. Again, the reaction that you're going to need, though, you're going to have some kind of compound given here. And if I say complete combustion, it means it's reacting with O2 to form CO2 and water. So all I have to say is this reactant, complete combustion, and you know the rest. Let's work an example with that, though. So we've got an example here that says, write the complete balanced equation for the complete combustion of ethane, C2H6, and oxygen. And so it's telling me complete combustion right away, and it's telling me ethane, C2H6, and it is saying an oxygen. Now, I don't have to say an oxygen. It's implied by complete combustion, but I did write it. So that part's cool. It gives me the formula for ethane, and it tells me ethane is C2H6. I do not expect you to know this yet, but ethane is a gas. I would not expect you to know that if I did not write ethane gas in the question, though. Some students would know it, like propane gas is what's burning gas in like grills if you're grilling at your house. Butane gas is what's burning lighters. Anything smaller than that would be a gas phase, but I wouldn't expect you to know that yet. I know this is reacting in the presence of O2, oxygen is gas, forming CO2 and water. And I'm going to move this over. Okay. Now, what I'm going to do first, I'm going to figure out how many of each species do I have in the reaction on each side of the reaction. So I'm going to write carbon, hydrogen, oxygen. And actually, I'm going to move this over so I can try to line this up a little bit. And then here, I'm going to write carbon, hydrogen, oxygen. So the left-hand side representing what's on the reactant side, the right-hand side representing what's on the product side. And the first thing I'm going to do is just write down what the reaction shows me. I know that I have 2 carbons here, 6 hydrogens here, and 2 oxygens here. On the other side, I have 1 carbon, I have 2 oxygens here, 2 hydrogens, and another oxygen here. So overall 3 oxygens. So nothing is balanced. I definitely need to balance, well, everything. I'm going to balance my oxygen last. And I'm going to do that every time when I do complete combustion, because when I have diatomics, they can cause problems sometimes. I see my carbon, 2 carbon on the reactant side, 1 on the product. So I'm going to say, okay, what if I multiply that by 2? I'm going to put a 2 in front of that CO2. That gave me 2 carbons, but that also changed my oxygens down here. Now I've got 4 oxygens plus that 1, giving me overall 5 oxygen. Now I'm going to balance my hydrogens. I've got 6 on my reactant side and only 2 on my product side. So I'm going to say, okay, what if I multiply that by 3? That's going to give me 6 hydrogen on each side, but that unbalances what I had written down for oxygen. Now I have 4 plus 3 giving me 7. When you have an odd number like that in a diatomic, the easiest thing to do is to do a fraction and then undo the fraction through multiplication. Once you get it, it's really easy to do, but it's hard to see it when you're first seeing it. So if it's confusing you now, that's okay, but I want you to practice it because it gets easier. Once you start seeing the pattern, it's a lot faster. What I mean by that is I've got a 2 over here and a 7 over here. I can play with this and take more time and balance it out, yes, or I can do a fractional method and then undo the fraction. I'm going to take the bigger number and put it in my numerator and the smaller number and put it in my denominator. 7 halves O2 gives me, if I have 7 halves of O2, that's giving me 7 oxygens on my other side. This is, 7 over 2 is 3.5. 3.5 times 2 is 7. So by doing the bigger number in my numerator, the smaller number on my denominator, I have balanced the reaction, but I can't leave it in fractional form. So what I'm going to do is I'm going to take the entire reaction, wrong button, and I'm going to multiply through by the factor in the denominator. So I'm going to take that entire reaction and I'm going to say, okay, I'm going to multiply through this entire reaction by 2. Because again, I can't leave the reaction with fractions. I want to undo that denominator. If I multiply through this entire reaction by 2, I end up with 2 C2H6 gas, 7 O2 gas, because that 2 cancels with this 2, 4 CO2 gas, and 6 H2O liquid. So I'm going to move this down under here so we can see that. But let's go ahead and check to make sure that we actually are still balanced once we did that. I've got carbon, hydrogen, and oxygen, carbon, hydrogen, and oxygen. Some people like balancing by math. I don't care. That's fine. Like if you want to use an algebraic method to balance equations, completely fine. I don't mind at all. If you do the method I'm doing where I'm just adding up the atoms under each one, make sure I usually use the first equation to write out my elements in order, but then make sure I'm matching to the same element on the other side. Because if I look here, I've got carbon, then oxygen, and that can throw students off because they're not reading the equation well. I've got 2 C2H6, so 2 times 2 for the carbon is 4. 2H6, overall 12 hydrogens. And 7 times O2 is 14 oxygen. On the other side, 4 CO2, so 4 carbon. 4 times 8, or 4 times 2 for oxygen, overall 8 right there, but I'm not done with oxygen. 6 H2O, so 6 times 2 for hydrogen is 12 hydrogen. And then 6 oxygen here, 8 plus 6, giving me overall 14. Every species matches. So this is my balanced equation. 2 moles C2H6 reacts with 7 moles of O2 gas to produce 4 moles of CO2 gas and 6 moles of water. Again, the reason I have to change that is I can't leave a balanced equation in fractional form, at least not in Gen Chem. We won't accept it. It's for a very specific type of reaction. Any questions on that so far? Okay. The next one says when the balanced equation for the complete combustion of ethanol, CH3CH2OH, is written using the smallest whole number coefficients, what is the coefficient of oxygen? So I've got CH2 or CH3, CH2, OH. Ethanol is a liquid. It's actually the alcohol that people drink. O2, gas. Give me CO2 gas and water. Because again, complete combustion always gives the same products. Some space there. Normally, I just balance this straight out. But the thing that students miss most often here is they miss the little oxygen right in here. They forget that it's there. So I recommend, until you get comfortable doing these, rewriting formulas like this. They're written like this because it's the way the molecule's connected. It's a very organic way to write it. I recommend rewriting it and putting your elements together. So C2H6O, I've got 2 carbons, 3 plus 2 plus 1 hydrogen, and then 1 oxygen. You don't have to do that. But I find that students who do that, sorry, I didn't mean to erase everything. I find that students that rewrite it are going to more likely to get the correct answer because they're not missing the oxygen in the middle of that ethanol. I miss the oxygen in the middle of ethanol when I balance this sometimes if I'm not paying attention. So I recommend doing that because I think it'll just give you a better time. My carbons, my hydrogens, my oxygens, my carbons, my hydrogens, my oxygens. I'm starting out with 2 carbons. On my reactant side, I'm starting off with 6 hydrogens and 3 oxygens. On the product side, 1 carbon, 2 hydrogens, 3 oxygens. So my oxygens are balanced, but they're not going to be balanced very long because I'm going to have to balance everything else. I'm going to go ahead and say, okay, well, let's balance my carbon. Put a 2 in front of there. Of course, that changed. I really need to change the size of that. That changed my oxygens. Now I have 4 plus 1, giving me 5 oxygen. Let's balance my hydrogens. I've got 6 and 2, so I'm going to say times 3, giving me 6 hydrogens on each side. So carbon's balanced, hydrogen's balanced. But that gave me another 3 oxygens, overall 7 oxygens. Now students look at this and be like, okay, well, now I have 7/3. Am I going to do a fraction with 7/3? The answer is no. My oxygen is split across 2 atoms. And so it might be helpful to write it like this, 1 plus 2, giving me 3, so I can see it a little bit better. But what I'm going to do is I need 7 on this side. Well, I have 1 hanging out here by itself. So what I need to do is make this into 6. Overall, that will give me 7. If I put a 3 in front of here, I've got 1 oxygen in my ethanol. I now have 2 times 3, or 6 oxygens in my O2, giving me my overall 7. So combustion reactions can be hard because it can be confusing on when do you use a fraction and when don't you. Truthfully, it just comes down to practice. I can't tell you which element will need it and which one won't. There's probably a pattern to it that I just haven't figured out. To me, it feels random. There probably is a pattern. I don't know what it is. Practice it and see. But I highly recommend rewriting it like this when you're doing something where I give you the formula written out like this. Another example is acetate is one of your polyatomics you need to know. I always write acetate as CH3COO-. It's the organic way to write it. And I'm just trained that way. Most students are going to memorize this as C2H3O2-. That's fine. I don't care. I accept it that way. I know what it says. My brain just doesn't write it this fast. Writing it this way, putting the elements together is easier when balancing equations than this way. Because again, students miss, and I miss, that little oxygen in the middle, and then I balance it wrong. So be careful of that. Okay, so reaction stoich. I know you've heard the word stoichiometry this week. I say stoich for short because stoichiometry is kind of a mouthful. But reaction stoich is using the coefficients in that balanced equation to determine the quantities of the chemical reactions. How much am I consuming or how much am I reacting? How much is being produced? but you have to have a balanced equation to do this. So again, we talked about, solid aluminum reacting in air to produce aluminum oxide. Here I've got a different example. I've got solid aluminum reacts with hydrochloric acid to form an aqueous solution of aluminum chloride and hydrogen gas. So kind of what we talked about a minute ago, can I take those words and bring it into a balanced equation? It's telling me solid aluminum. So I know Al solid. It's telling me reacts with hydrochloric acid. Now, you guys are going to learn naming on acids. You're also going to just memorize hydrochloric acid very quickly if you don't have it already, because it's one of the most common examples we use in class. But hydrochloric acid is HCl, and acids are aqueous phase because they're things dissolved in water. Hydrochloric acid is actually HCl gas dissolved in water, bubbled through water. It forms an aqueous solution of aluminum chloride. Aluminum chloride is AlCl3. We know it's aqueous, it just told us so, and hydrogen gas. Hydrogen is one of our diatomics. So now I've got all my species. I balance out the reaction. And I see that I got 2 aluminums reacting with 6 HCl's to produce 2 AlCl3 and 3 H2O. So what does this mean? It means we can derive those mole-to-mole ratios. I can't write that low on my screen, so I apologize. But I can say here things like 2 moles of aluminum to every 6 moles of HCl, because for every 2 moles of aluminum reacted, 6 moles of HCl will also react. I could say 2 moles of aluminum to 3 moles of H2. And students kind of get thrown off by that one. So but aluminum and H2 have nothing in common. They don't directly, but 2 moles of aluminum are required to produce that 3 moles of H2. If that 2 moles of aluminum is not present, the HCl will not react with it and will not form H2. I could say 2 moles AlCl3 to 6 moles HCl. For every 2 moles of aluminum chloride produced, 6 moles of HCl has been consumed. So let's work. We're going to do the last last handful of slides. We got 4 or 5 slides. We're going to do some examples. First one is what mass of oxygen gas is required for the complete combustion of 29.0 grams of butane C4H10. This little picture here is from your textbook, and it's very much just a way to kind of remember the pattern that we follow to do these reactions. Now, I recommend bringing some kind of highlighter or something to your assessments, because some of the questions we're going to give you are long. They got a lot of information. You spend time reading the question, then you have to go back and figure out what was important in that question, because you don't realize that the first time you read it. And your quizzes are 10 minutes in class. Well, depending on which class you're in, they're 10 minutes if you're in Gen Chem, they're 15 minutes if you're in engineers. And the engineering quizzes have more material on them than a Gen Chem quiz does because of the time limit. So they're fast. 15 minutes or 10 minutes go really fast when you're stressed out. Bring a highlighter, highlight what's important and what you're given. I am asked, what is the mass of oxygen gas required for the complete combustion of 29.0 grams of butane C4H10? So I'm trying to find mass of oxygen gas. It's telling me it's undergoing complete combustion, and it's 29 grams of butane. I'm not given the balanced equation, so I'm going to have to find the balanced equation. I've got C4H10 reacting with O2 gas, forming CO2 gas and H2O. So my carbons, my hydrogens, my oxygens, my carbons, my hydrogens, my oxygens. I've got 4 carbons, 10 hydrogens, and 2 oxygens on my reactant side. I've got 1 carbon, 2 hydrogens, and 2 plus 1 or 3 oxygens on my product side. I'm going to balance my carbons. Times 4 here is going to give me 4 carbons here. Of course, that changed my oxygens here. I now have 8 here. I'm going to balance my hydrogens. 10 versus 2. I'm going to say, okay, I'm going to multiply this by 5, giving me 10 hydrogens on each side. But of course, that unbalanced my oxygens. So my carbons are done. My hydrogens are done. Now I've got a 2 to 13 ratio. If you've got 2 on the reactant side and a bigger odd number on my product side, And the 2 on the reactant side is for a molecule that is together, meaning not split apart, the oxygen is not split across 2 different molecules. Fractions are easiest. I'm going to do 13 halves because 13 halves O2 gives me 13. It is now balanced. I can't leave it this way, but the reaction is balanced. So I'm going to go through, I'm going to multiply the entire reaction by 2. And then I'm going to quickly check to make sure that my bookkeeping is correct. On the reactant side, I have 8 carbon. Product side has 8 carbon. Reactant side has 20 hydrogen. Product side has 20 hydrogen. Reactant side has 26 oxygen. Reactant side has 16 plus 10 or 26 oxygen. So I've confirmed that my reaction is balanced. Now I can go ahead and actually answer the question. Sometimes we'll give you a balanced equation, sometimes we won't. Sometimes we're just going to give you words. It depends on what we're trying to assess you on. Just like in dimensional analysis, the first thing I'm going to write down is what I'm trying to find. I'm trying to find the grams of O2. How do I know that? Because it says mass, and mass is not moles. I know I'm going to want grams. I've got 29.0 grams C4H10 reacting. We cannot compare grams. 1 gram of C4H10 does not have the same number of molecules as 1 gram of O2. We have to convert to moles. So I know 1 mole C4H10, and I add up its molar mass, and I find the molar mass of C4H10 to be 58.12 grams. I've canceled out my grams of C4H10. Now I can go on and I'm in moles. Now that I'm in moles, I can use my balanced equation. And I'm trying to convert between C4H10 and oxygen. I see that 13 moles of O2 are reacted for every 2 moles of C4H10 reacted. Cancel out my moles of C4H10, get my moles of O2. Now I'm going to go ahead and convert to grams of O2. I know that 32 grams of O2 is 1 mole of O2. And I get 104 grams of O2. My initial value here had 3 sig figs, so my final value has 3 sig figs as well. And so if I want to react 29 grams of butane, it's going to require 104 grams of O2. Any questions? Another thing we do a lot, and students hate this part, but this part is absolutely vital to what you're doing because you're going to see it all throughout Chem 1 and then it comes back heavy in Chem 2, is this concept of a limiting reactant. Basically, what I mean by that is if I am given amounts for both reactants in a reaction, I have to decide how much product I can actually make. One of them is going to run out, limiting how much product I can make. It's kind of like, if you go and wash, let's say you go wash all your socks, but one sock disappears somewhere in the wash cycle. It's kind of like the joke of the world, right? That your Tupperware lids and your socks go missing. And so say I put in 26 socks, but I only get out 23 socks and I'm trying to pair them up. I can't pair up my socks anymore, especially if a pair went missing that was the actual pair, like colored pair. I can't mismatch my socks. It drives me nuts. And so something is limiting me finishing that, probably me finding the sock that's missing. Sorry. Very good question. On the last one, it said, would you say 100 grams? I have a private question asking, would I say 100 grams since I started with 29? And the answer is no. And the reason, 2 things. 29.0, when I have it written as 29.0, that 0 is significant. So that, oh, you're good. But I also want to say, if I had actually started with 29, that has 2 sig figs. And so if you write 100, that only has 1 sig fig. So because we have done this to you, not even on purpose all the time, to be honest with you. Students think it is. It's not always on purpose. If you saw something that said like 29 and the answer was 100 like this, you would have to write 1.0 times 10 to the 2 to get to the correct sig figs. But so your limiting reactant is what's limiting your reaction. So common questions we're going to ask you is, which chemical is your limiting reactant, how much excess reactant remains after the completion of a reaction, and how much product can be formed. We do this through stoichiometry, but through determining our limiting reactant. And so like the picture is shown here, if we're trying to take H2 and O2 to produce water, H2 plus O2 produces water. Here I've got 4 molecules of H2, 3 molecules of O2. And so some students will look at it really quickly and say, well, I have less O2. That must be my limiting reactant. We find it's actually not, because our product, our water, requires 1 oxygen for every 2 hydrogen. This and this make 1 compound. This and the other half of the oxygen make a second compound. This and this make 1 compound. This and the other half of this oxygen make 1 compound. Overall, we have 1 oxygen molecule left over. So we always have to be cognizant of what is our actual limiting reactant. And students have a hard time with it because it's not always the easiest to see it within the math. Sorry, I'm trying to pull up so I can actually, I have the answers written out here, so I have to rewrite them all. And it's small on my screen. We will follow a pattern, and where is it? I have it up here. This I don't have in the PDF that I'm sharing with you guys right now. I just didn't think to put it in there. This is the pattern that we're going to follow in my class and Dr. Fry's to teach how to limiting reactant. A lot of students have learned a different pathway in high school, and truthfully, I don't care how you do it as long as you get the right answer. It doesn't bother me either way. But I want to walk through this pattern because when students aren't good at doing limiting reactant problems, this is the best way to follow it. So first step, convert what you're given to moles. Second step, we ask ourselves, if we use up all of one of our reactants, how much of the other reactant remains? Or how much of the other reactant will I need? We answer the question in step 2 by using the multiple ratios of the reactants and the balanced chemical equation. And again, I'm going to show you what I mean by this in a second. We ask ourselves, do we have it? Do we have enough to do this? And from there, we can assign the labels of limiting or in excess to the different reactants. Then we use limiting reactant to solve the original stoich problem. So in the balanced equation below, so it is balanced, that part's nice. How many grams of solid iron, so I'm trying to figure out how many grams here, can be formed if 50 grams of Fe2O3 or iron 3 oxide reacts with 10 grams of CO or carbon monoxide. Now, what we need to figure out is which one is our limiting reactant. Now, some students are just going to automatically guess that CO is the limiting reactant because it has the smaller amount of grams. And it may be. I don't know, though. That's what I have to find out by math. So when you are given values, when you are given the amounts for 2 or more reactants, it is a limiting reactant example. We're given amounts for 2 different reactants, for both reactants in this case. In that case, it is a limiting reactant example, and you have to follow the steps to figure out what's actually going to limit your reaction. So let me see how I actually solve this one, because every time I solve these a little bit different. And I don't feel like redoing the math. Okay, so the way I solved it is not actually following the flowchart that I just showed you. I'll show you how to do that in another problem. On this one, I just compared the 2 to each other. So I said, kind of did the flowchart, but quicker. I said, well, how many grams of iron is produced if Fe2O3 is my limiting reactant? LR means limiting reactant. So if I started with 50 grams Fe2O3, convert that to moles of Fe2O3. And the way I'm doing it now is most likely the way you saw it if you did this in high school. This has a molar mass of 159.7. By the balanced equation, I can see that 2 moles of iron will be produced for every 1 mole of Fe2O3 consumed. I'm going to go ahead and say 55.85 grams of iron to 1 mole of iron. And I will move this down the screen in just a sec, but it's so much easier to write at the top. That cancels my moles of iron, my moles of Fe2O3, my grams of Fe2O3, and I'm left with grams of iron. Again, I don't know if this is the right answer yet, but let's move it down here so I can actually finish writing on it. Calculate this out, and I'm going to get 35.0 grams of Fe. I'm going to do the exact same thing with how much CO2, or with the CO2. So if the CO2 is the limiting reactant, how would that work? I have 10 grams of CO. Convert that to moles of CO. CO is 28 something, 28.01. I look at my balanced equation, and I see that 2 moles of iron are produced for every 3 moles of CO. 55.85 grams of iron for every 1 mole of iron. Make sure your stuff is canceling. I've got moles of iron canceled, moles of carbon dioxide or monoxide canceled, and grams of carbon dioxide canceled. I calculate this out, and I get 13.3 grams of iron. Move this down. Again, sorry, you guys, it's just really hard for me to write on the bottom of my, or closer to the bottom of my screen. I compare these two numbers. Whichever one makes the smaller amount of iron is the limiting reactant. So CO is my limiting reactant. That means that Fe2O3 is my access reactant. Now this question is actually saying, what is the access reactant and how much access remains? I've answered half the question. I've answered which one is my access reactant. The access reactant is that iron 3 oxide. I have not, however, answered how much actually remains. There are a few different ways we can solve this question as well. So what I'm going to do, I just got a private question saying, do we need to convert both answers to moles? Not specifically sure what you mean. If you're just trying to find like access and limiting reactant, you can actually stop right here and compare how many moles you have of each species of the product. And that will tell you which one is your limiting reactant as well, because it's a smaller number of moles. I've converted both to grams just to make it easier, because most students will convert all the way to grams. But if I stopped right here instead, I would have converted to moles for both. But I'm not sure if that answers your question. So if it doesn't, feel free to rewrite it or rewrite something that something else so I can help clarify. On this one, so I want to figure out how much remains. I know that CO2 is my limiting reactant, and there are a number of ways we can do this. But what I'm going to do is I'm going to compare my limiting reactant to my access reactant and see, well, since I know what my limiting reactant is, how much of my access reactant do I need to use it all up? So I'm going to say, okay, well, number of grams of Fe2O3 needed to react my CO. I've got 10 grams of CO. Now, if I would have converted to moles here in the first place, like the flowchart says, I wouldn't have to go back and do it right now, which is what makes that flowchart easier. 1 mole of CO, 28.01 grams of CO. I know based on the balanced equation that 1 mole of Fe2O3 is reacted for every 3 moles of CO reacted. So that gets rid of my moles of CO, my grams of CO. I'm now into moles of Fe2O3. So again, if I had converted to moles in the first place, I'd be able to tell right now how many moles are left over. But I didn't do that because I didn't make my life easy when I wrote this out a couple of years ago. 159.7 grams of Fe2O3 to 1 mole of Fe2O3. This gives me an answer of 19.0 grams of Fe2O3. But what does this answer mean? This answer is the number of grams needed or reacted with all of that CO2, carbon monoxide. So we need 19.0 grams Fe2O3 to react 10.0 grams of CO. I have to move that up. I can't write that low, it hurts. We are starting with 50 grams. Of Fe2O3. So the difference is how much excess we have. 50.0 grams minus the 19.0 grams reacted. I will have 31.0 grams of Fe2O3 in excess. Why do I care? Look, to be honest, if I'm going to do this reaction and I need a little bit of excess reactant, yes, but if I only need 19 grams of Fe2O3 to make the reaction go, I'm not going to dump 50 grams into it. It just costs money. It's just wasteful chemicals. And so it's nice to know how much we actually need and how much is in excess, so we can see what do we need for the reaction to go, yes, but to also be realistic on what we need to do. Any questions on that one? Okay.
I thought that the excess was 35 grams of Fe or iron.
No, sorry. So that's a good question. So what that 35 grams is, and I know the slide's getting really messy, I apologize. What this 35 grams is here is how much iron I could have made if I reacted all of the iron 3 oxide. So if nothing else limited the reactant, that 35 grams would be how much iron is produced based on 50 grams of iron 3 oxide. And so what some students will do is they will take another way you can do it mathematically is, I don't have any room, but I could take the difference between these two numbers here. So I could take 35.0 grams of Fe minus 13.3 grams of Fe, and then take this answer and convert it back to grams of Fe2O3. Because basically, if I used all of my Fe2O3 up, I would make 35 grams. I can't make 35 grams because my CO is running out first. So the difference between these two numbers is how much Fe2O3 will never be used up, the 31 grams, because I can never make that amount of iron. Does that make sense?
Yes, thank you.
Common thing, Caitlin, I promise. And so I promise you're not the only one that's confused either, because this is figuring out the amount of excess reactant is absolutely the most difficult thing for my students to do. Chem 1 doesn't matter. Chem 2, we figure out a different way to do it. And so if you are really struggling, I don't care whose class you're in, mine or Dr. Fry, if you're really struggling, come to me. I have a different way I can show you how to do it, but I don't show most students because it doesn't click for everyone. Some students really struggle with it. And so if you're really truly struggling and you can't figure it out, come see me. I do not care whose class you're in. I will help you find a different pattern. I promise, but they're hard. Okay. We're also going to oftentimes work questions like this where students hate these questions, but we love them because we think they're fun. They're like a puzzle. That almost makes it worse. A 3.41 gram sample of a metallic element M reacts completely with 0.1058 moles of a gas X2 to form 4.52 grams of MX. What are the identities of M and X? Students read this and just like, I don't know, I don't care, I don't want to do this. I get it. But we find them fun because for us, again, it's like a puzzle. So I want us to think about what's happening here. We've got some metallic element M. We usually use M for metal. So we've got M reacting with a gas X2, and it's forming a compound MX. I'm told that 3.41 grams of M reacts with 0.0158 moles of the gas X2 and forms 4.52 grams of MX. How can I figure out their identities? Well, I know that the M is a metal. I know the X is a non-metal because it tells me it's a gas, which means it's a non-metal, okay? The only metal that that's not in a solid phase is mercury, and that's a liquid. So I know that this has to be a non-metal. And it also has that subscript 2, which means it's a diatomic. So I've already narrowed it down to one of 7 possibilities. H2, N2, O2, F2, Cl2, I'm running out of space, Br2, I2. I know it's one of those. But how can we determine their identities? The easiest way to determine identity of something is determine its molar mass. And this comes in all of chemistry, all of Chem 1, all of Chem 2. I'm giving a test tonight in Chem 2. It's their third exam covering all of the last 2 chapters. And they have a question on their test that basically they have to figure out their molar mass of something. And students forget how simplistic, I don't know what the right word, molar mass is to calculate. Remember, your molar mass is your grams over your moles. And so we're going to use the information we have to solve for molar mass of each species. So let's go ahead and look at X first, or look at M first. We know that it's some metal, but we've got a balanced equation here, or we've got not a balanced equation yet. We're going to soon have a balanced equation here. I apologize. I know that M forms MX. I got to balance this thing. 1M, 1M. Looks good, right? 2X, 1X. Doesn't look so good. I'm going to put a 2 in front of here to balance out my X's. But that means I have to put a 2 in front of here to balance out my M's as well. Now I have a balanced equation. I know 2 moles of my metallic element M react with 1 mole of my diatomic gas to produce 2 moles of my MX compound. So if I'm trying to find the number of moles of M, I have a balanced equation. I can do this now quite easily, actually. 0.0158 moles of X2 times 2 moles of M for every 1 mole of X2. This tells me I have 0.0316 moles of M. Now I can use this. I can say, okay, I have 3.41 grams of M. I just figured out that I have 0.316 moles of M because of the reactant. If this, if M reacts with 0.0158 moles of the gas, the diatomic gas, then it has to be this many moles reacting. And I get a molar mass of 107.9 grams per mole, which when I look it up on the table is silver. So I know my metal. I know it's Ag. I still want to figure out the overall compound though. Now I've got to figure out how can I determine the identity of X. I'm gonna have to move that up. Conservation of mass. I know that if I know that anything that reacted isn't created nor destroyed. So conservation of mass I know that MX is 4.52 grams. I know that 3.41 grams of that came from M, which means the difference which 1.11 grams is from X, or the X2, or sorry, it's from X because it's my my product, it's X at that point. So I can use X to convert back and figure out what is my species. I'm going to take X, which is 1.11 grams, divided by the moles, 0.0158 moles, and I get an answer here of 70.3 grams per mole. The trick to this question, because it wasn't tricky enough, the trick to this question is remembering the fact that this is representing X2. This is the molar mass of X2, which means I have to divide that number by 2. Giving me 35. Which represents chlorine. So the actual balanced equation here, Ag solid, Cl2 gas, 2 of those, gives me 2 silver chlorides, which is a solid. So it's kind of pulling in stoichiometry, but also pulling in conservation of mass. It's one of the more, it's a challenging question because students don't see the puzzle pieces coming together. Are there any questions on this one?
Yeah, I had a question.
Mhm.
So there's some error in like the molar mass for chlorine we found compared to the periodic table. So do we just choose whichever is closest, or if there's too much error, can we like know
So
if it's
on
wrong?
this one, we know it has to be a diatomic. Okay, so because we have X2. So it could be rounding error. It could be when you do experimentally, nothing ever comes out perfectly. But since we know it's a diatomic, we have to pick whatever is closest to that mass. So 35.45 versus 35.1 is almost the same thing. And there's no other diatomic around it.
Okay, thank you.
That makes sense?
Yes.
But no, that was a good question because it's going to happen. It's going to happen where it's not perfect on the math all the time, especially when you guys get into lab. I know you guys won't have lab until second semester. Second semester, either take quant lab or gen chem lab. And sometimes I don't know what students do. Sometimes I do know what they did. Sometimes I have no idea what they did. And we have to play with the numbers to make them happen again. Other questions on this? I did have one more example that I'm not going to be able to have time to work, but I will, I'll post the key of it later, but I want you guys to see outside of this, see if you can work this one, and then I'll post the key separately so you guys can see it. But how much nitrogen gas is formed when 18.1 grams of NH3 and 90.4 grams of CuO are present. So this is a limiting reactant problem. So see if you can work it out. And again, I will post the key with it on D2L. Probably not for a day or two though, because I want some students to try to work on it first. Okay. Any other questions, concerns, comments, questions on this? Any other examples we've worked or anything? Okay.
I had one more question.
Mhm.
On the active chemistry assignment, the one called Stoichiometry 2, out of the 11 questions, one of them was predicting a reaction. I think you said we'll like learn that next week.
Yes.
It was just really difficult, but I was wondering if I should be able to do it.
Normally we haven't done it yet intentionally. Sorry, 1 second. I'm trying to answer you and I'll answer the private message just a sec. Normally we wouldn't have you do those problems yet, but I didn't pick the active chemistry. So whoever picked it probably didn't think about it. I wouldn't worry too much if you're not being able to do that one correctly yet. Because
Okay.
yeah, we have not covered in, it's a good question, Reagan. Basically, reaction predicting comes in chapter 5. And so the way boot camp is designed is every week is one chapter, except weeks 5 and 6 are both chapter 5, because chapter 5 is massive. And so
All
yeah,
right.
we didn't get to it till next week.
Okay, thank you.
Thank you. Okay. Any other questions or comments or concerns that you guys have before I let you guys go today? Thank you. Okay, well, keep working. I see your activity in D2L, so keep it up, keep working really hard. You guys are doing great. I know that Dr. Green posted about it, but she wasn't kidding. If you continue through boot camp and complete, you'll have to look at her percentage. I think it's 70%, but I'm not positive of boot camp. By the end, you get the t-shirt. And I'm not kidding, students love the t-shirt. We see them on campus all the time, and they're really, really soft. They really are. You're gonna get lots of free t-shirts at TCU. It's just the way life works there. But the boot camp one is definitely a coveted shirt. So make sure to keep involved, at least get your t-shirt out of it. And then she's also doing drawings. I know we already had 2 students win $100 to the big bookstore. We might have another drawing coming up. So just to try to keep encouraging you guys to keep going, keep being involved, okay? Thank you. I hope that this was helpful, and I look forward to seeing you guys next week. Thank you.
Thank you.
Thank you.